In this module, we will begin to discuss electromechanical systems, in particular sensors. So far in this course, we've modeled electrical systems and mechanical systems. In this module, we will begin to discuss systems that have aspects of both electrical and mechanical systems, i.e. electromechanical systems. We will first begin with sensors in this module, and in a subsequent module we will talk about electromechanical actuators. In this module we will also talk about how the sensor fits into the larger measuring system and how the aspects of the measuring system affect the analysis and design of control systems in general. Most control systems, including automotive control systems, include electrical and mechanical components. Here in the figure shown, we have an example feedback system with the typical elements of a control system. If we look at this, there are components that are in the electrical domain and there are components that are in the mechanical domain, and we need components that are able to convert between these two domains. For example, the controller itself is usually implemented in the electrical domain, either as a circuit or in software, while it might be the case that the system that's trying to be controlled is a mechanical system. For the purposes of discussion, let's presume that we have a cruise control system. So in this situation, you could imagine that the driver has some sort of knob or something on the dash which he uses to set the desired speed for the cruise control. And so what he needs is some sort of device that converts the turning of the knob into an electrical signal that can be read by the electrical controller. That controller then generates a voltage which controls an electromechanical system, for example a motor that's attached to the throttle valve. And so by changing the voltage, the controller affects the setting of the throttle, thereby allowing more or less air and more or less fuel into the engine. That in turn causes the engine to change speed. That speed, which is a mechanical quantity, then needs to be converted back into an electrical quantity in order to be read into the controller. And that needs to be done with an electromechanical sensor. So for this particular example, where the controller is implemented in software and we're trying to control a mechanical system, we need three electromechanical quantities: a transducer, and a sensor, and an actuator. In this module, we will in particular discuss sensors and transducers, and in a later module, we will discuss electromechanical actuators. At this point, we'll now go ahead and list a few examples of sensors and transducers that are electromechanical. Go ahead and take a second and think to yourself if you've encountered any examples of sensors or transducers that are electromechanical in your job or in previous coursework. One class of electromechanical sensor relies on piezoelectric materials. These are special materials that produce charge when deformed, for example quartz crystal. These can be used in things like an accelerometer to measure acceleration, in a microphone to measure basically sound. The microphone generates a voltage output in proportion to the pressure wave created by a sound wave. Load cells can also use piezoelectric materials to measure force. Another class of sensor works on the basis of the fact that electrical properties of some materials change with mechanical properties. For example, a thermistor works on the basis of its resistance changing with temperature. A strain gauge works on the basis of its resistance changing with deformation or stretching. And pressure transducers generate electrical signals in proportion to pressure based on changes in resistance or capacitance or inductance, depending on the construction of the transducer. Other sensors rely on electromagnetic induction. That is, that the motion of a conductor through a magnetic field can induce an EMF, a voltage. Examples of these include LVDTs, linear variable differential transformers, and resolvers. A final class of sensors relies on special materials that produce charge in response to light. This includes optical encoders and digital cameras, consisting of an array of CCD elements, charge-coupled devices. At this point, we'll go ahead and pick a few example electromechanical sensors that are of particular importance to automotive and electric vehicle applications. A common, inexpensive type of sensor used in many applications is the potentiometer. With the potentiometer, the mechanical quantity of position is changed into a change in resistance. And in particular, it can be used as a voltage divider to generate a voltage that's proportional to the change in position. One automotive application of such a sensor is to measure the position of a pedal. So looking at this figure, we have a resistance element. And that resistance element has a total resistance R. As the slider moves, it changes the amount of resistance on the left of the slider and on the right of the slider. And if we apply a voltage across the potentiometer, then the voltage that's generated at the output will change as the slider changes. The circuit diagram representing that is shown below, or simply it all derives from Ohm's law. So we have some constant voltage E sub I, we have some constant total amount of resistance R, and so the amount of current through the potentiometer is a constant amount I. As the slider moves, the amount of resistance R2 changes, and that causes the amount of voltage across R2 to change. So more specifically, the output voltage is equal to R2 times the current through the resistor, which follows from Ohm's law. The input voltage, however, is across both R1 and R2, which are in series. And if you think back, when we have resistors in series, their resistances add. And so the ratio of the output voltage to the input voltage is shown here, where the currents cancel, and we get this relationship that shows how the change in pedal position, or the change in angular position of the slider, causes a change in the output voltage, which can be measured. This concept of a voltage divider was also introduced when we were talking about complex impedances. Another type of sensor is the optical encoder. And this type of sensor can be used to measure displacement or velocity. So specifically, the optical encoder consists of a light source called the emitter, and it generates some light, and then there's some material that has gaps in it between the emitter, and on the other side we have what we call the detector. So as this material moves, it alternately blocks the light and lets the light through. When the light is able to go through one of these gaps and reach the phototransistor, the phototransistor acts like a switch and it closes, and it causes the output to go high. When the light source is blocked by this material, then the phototransistor acts like an open switch and the output goes low. And so by counting these pulses, we are in essence able to count the number of gaps and blocks that move past the light source. And that gives us an indication of the displacement of this material. If we look at how many pulses we count in a certain time period, then that frequency gives us a measure of the speed of this material. Furthermore, if we have multiple pairs of emitters and detectors that are offset from one another, we can also measure the direction that the material is moving. And that's shown in this slide. So in this slide we have a rotary encoder. So we have this disk of material with gaps and blocks. We can also have linear encoders, but in this case we've got a rotary encoder. We have two emitter detector pairs, one located at point A and one located at point B. When this disk is moving counterclockwise, what will happen is this material will block the pair at location A first and then the pair at location B second. And so when it blocks the pair at A, that channel will go low. Then subsequently the channel at location B will go low. If we're rotating in the opposite direction, however, clockwise, then this material will hit the pair at location B first, then the pair at location A second. Therefore, channel B will go low first, and then channel A will go low. Therefore, looking at these two pulse trains, looking at which of the pairs goes low first, we're able to determine the direction that the encoder is moving. If we add additional channels, we can also improve the resolution of the encoder. How many pulses we get for a given change in angular displacement.